Hello everybody, it's Tarun. Welcome to your 13th tutorial in the Signal System and Control course. In the last tutorial, I taught you about the convolution property and the frequency response and impulse response related with it. And so I taught you some examples also. Okay. And in this tutorial, I will teach you about the multiplication property. Okay. And I'll teach you the frequency response and something called linear constant coefficient differential equations. Okay, so now let's get started. So first I'm going to teach you the multiplication property. Okay, the multiplication property is the dual or opposite of the convolution property. Okay, in the convolution property, we convoluted the signals in the time domain and the signals get multiplied in the frequency domain. Okay, but here if we are multiplying the signals in the time domain, okay, as you can see here, like RT is equal to ST into PT, and in frequency domain, they are convoluted and are multiplied with 1 upon 2 pi. As you can see that R of j omega is 1 upon 2 pi S of j omega convolution P of j omega. Okay, so what does it say? That multiplication in time domain implies that convolution in frequency domain. So multiplication of PT with ST is called scaling or modulating amplitude of PT, okay, with amplitude of ST, okay, and multiplication is often referred as amplitude multiplication because we can multiply two signals to just modulate the amplitude of a particular signal, okay. And this multiplication property is also referred as modulation property. Okay, so now let's see some example. Multiplication with cosine. First thing is modulation, in which I am going to multiply signal ST with cosine. Okay, I am having a signal ST whose spectrum in frequency domain looks like this. Okay, and I am having a carrier signal, which is a term referred in the modulation scheme, which you will learn more in the principles of a communication course. Okay, I am taking it the signal PT as under root 2 cos omega naught t. Okay, so if I find the Fourier transform of this signal, then I can find out it with the help of the Fourier transform for periodic signals, which will look like this. Okay, and P of j omega will be will look like this in the graphical manner. So the modulated signal RT-ST with spectrum RJ will look like this. Okay, and mathematically if I try to find out, then it will be 1 upon root 2 S of j omega minus omega naught plus 1 upon root 2 S of j plus omega omega naught. Okay, this is so because if I am convoluting some S signal with delta signal, okay, which is there, delta signal or unit impulse signal, then I'll get this type of result. Okay, and I'm taking assumptions that omega naught is greater than omega 1, which implies that there is no overlap. Okay, and RT uniquely represents ST, and it is called sinusoid amplitude modulation. So if I again multiply this signal with cosine, then it will get demodulated. Okay, so the demodulation technique I am not going to tell you. It is very simple, just similar to the above multiplication with cosine. So you need to do it yourselves. Okay, but one more thing is that here, after multiplying it with cosine, I will pass this signal through a low pass filter to just get the desired output. Okay, we are having 3 loops or lobes here. Okay, and we need this part as a desired output because our original signal contained only this thing. Okay, and it did not contain this part and this part. So I will pass it through a low pass filter with frequency range minus omega 1 to omega 1, as you can see here. Okay, which will remove these parts from the signal. Okay, So now let's see next example. where I am having xt as sin t into sin t by 2 upon pi t square. Okay, I can write xt as product of two sinc functions. Okay, in this manner, or you can remove the pi from here. Okay, it is not necessary you use the pi, but here I have used. So with the multiplication property of Fourier transform, I can find that x of j omega will be 1 upon 4 pi square. This is because 1 upon 2 pi is also there in the multiplication property. Fourier transform of this function into Fourier transform of this function. Okay, or into convolution of this function. So I'll get this result because the Fourier transform of sinc function is rectangular function. Okay, and convolution of rectangular pulses gives us the trapezium. Okay, as you can see here. So this was the multiplication property, and now let's see the last topic in this unit, which is frequency response and linear constant coefficient differential equations. Okay, for this thing you need to recall these equations which I told you in the unit 1 for linear constant coefficient differential equations. Okay, the system is described by these equations. Okay, for a frequency response h of j omega, let's first apply or consider that xt is e to the power j omega t. Then yt will be h of j omega into e to the power j omega t. Okay, and alternatively you can see that with the help of convolution property, h of j omega will be y of j omega upon x of j omega. So if I apply the Fourier transform to this differential equation, okay, as you can see here, the summation and ak will move out. Okay, only Fourier transform of tk yt upon dtk, and similarly here Fourier transform of dk xt upon dtk will be required to determine. Okay, so you know that for dy by dt, the Fourier transform will be j omega into y of j omega. So for differential of kth time, okay, kth order, you can see that it will be j omega to the power k into y of j omega, and similarly here j omega to the power k x of j omega. So here h of j omega will be y of j omega upon x of j omega, which will be summation bk j omega to the power k upon ak j omega to the power k with summation over them outside. Okay, so here you can observe that h of j omega is obtained from differential equation by inspection, and h of j omega is a rational function in j omega. Okay, now let's see some examples. So first is stable LTI system, which is characterized by this equation. Okay, dy by dt upon dy by dt plus ayt is equal to xt, where a is greater than 0. So to find out the frequency response, what you should do, you take out the Fourier transform of this equation, which will be j omega into y of j omega plus a y of j omega is equal to x of j omega. So here you can see that y of j omega upon x of j omega will be 1 upon a plus j omega. Okay, and its impulse response will be by taking the Fourier inverse of frequency response, it will be e to the power minus at ut. Okay, so now let's see the second example where the LTI system is characterized by this equation. Okay, so similarly, as I told you in the first example, you need to take out the Fourier transform of this equation to find out the frequency response. So it will be j omega square y of j omega plus 4 j omega y of j omega plus 3 y of j omega is equal to j omega x of j omega plus 2x of j omega. Okay, so h of j omega will be y of j omega upon x of j omega, and it will be j omega plus 2 upon j omega square plus 4 j omega plus 3. Okay, and with the help of partial fractions I can rewrite this equation in this manner, and its impulse response will be half e to the power minus t ut plus half e to the power minus 3t ut, which is of the form e to the power minus 80 ut. Okay, and let's see the third example. Okay, I am having xt as e to the power minus t ut, and this is the system of last example only. Okay, where I have defined the input, and I have y of j omega, which is h of j omega into x of j omega, and I also have h of j omega from the last example only. Okay, and x of j omega will be 1 upon j omega plus 1. So you can see that y of j omega is j omega plus 2 upon j omega plus 1 square into j omega plus 3. With the help of partial fraction technique, I can rewrite this equation in this manner. Okay, and I can find out the value of a11, a12 and a21 as the method I told you in the last tutorial, which was to multiply this to find a11, to multiply this term with y of j omega and put the value of j omega equals to minus 1. Similarly, you can do for the rest. Okay, and after finding the values of a11, a12 and a21, you can find out the value of yt with the inverse Fourier transform, which will be this. Okay, so this was all from my side in this tutorial. Okay, and I have attached the assignment with this unit also, like I do with every unit. So I'll also suggest now also to do the assignment by yourself. If you have any problems, you can go through the book and hints provided. Okay, but don't go to the hints first directly. First try to do the questions by yourself. Okay, and if more problems, then there are more examples in the book, so you can see or refer to there. So thank you guys for watching. I'll see you in the next tutorial.